Uh, Thank you everyone for finding time and visiting today's webinar. I am Professor Sanjay K. Sharma, editor, RASAYAN Journal of Chemistry. RASAYAN Journal of Chemistry is a Scopus Index journal since 2008. VChemTalk is an initiative of RASAYAN Journal of Chemistry to popularize chemistry education and discuss the recent research updates in the area of chemical sciences. The RASAYAN Journal of Chemistry introduces a series of lectures titled VChem Talk. It will be beneficial for the students, research scholars, academicians, and entrepreneurs at large. We are delighted to host Professor Ramesh L. Gardas, Professor, Department of Chemistry, IIT Madras, as our inaugural speaker of the series. He will be delivering his talk on Ionic Liquids as Environmental Benign Solvents for Sustainable Developments. Before starting today's session, it would be my proud privilege to introduce our speaker. Professor Gardas is professor in IIT Madras, and he has more than 20 years of research experience. Professor Gardas' research group focuses on chemical thermodynamics and phase equilibria of industrial important solvents and their mixtures. His research group is unique in the country, focuses on both science and technology, part of contemporary field, ionic liquids, deep eutectic solvents as alternative more than 7,500 thermodynamic data points measured in his research wide range of temperature and pressure, which is referred to and extensively used by the peer scientific community as Gardas and Count. He has been recognized as associate editor of Society of Chemistry, Pablon Top Peer Reviewer Award 2019, and feature in the list of world ranking of two. Professor Gardas to please take over and start today's session. Professor Gardas.
Thank you very much, Professor Sanjay Sharma. And let me share my screen first. This will be streaming live on Facebook. So it's an excellent opportunity. So I put my talk for the beginners or those who are interested to know more about ionic liquids, or those who are interested to know how to replace the volatile organic solvent for this title, and there is a message for all of us to take forward in our own research field. And I put one 3R principle: reduce, reuse, and recycle. This is one of the important things when you talk about environmental benign. And I would like to thank RASÀYAN Journal of Chemistry and this VChemTalk series, all the organizers, for giving me this excellent opportunity. You will have a chance to discuss or share your views and ideas and ask me a few questions at the end. However,
Professor
if you don't,
Gardas, Professor Gardas,
Yeah.
there is a small submission. It is an announcement for the participants. If you have any question during the talk, you just send me that question in chat box, and we'll certainly ask those questions to the speaker at the end of the talk. Thank you very much. Professor,
so
please
as
continue.
informed by organizers, please do type your questions. And if you would like to ask me personally or later on, you can send me by email. That is gardas@iitm.ac.in. So let's go in to the next 1 hour. And I request the organizers to please take care of this admitting in, because keep on the messages popping up. So for any research to be a successful research or the fruitful research, we need innovative ideas, and we need knowledge to execute them, and we need dedication to work on them, and we need sufficient interest to work on them. Apart from the knowledge, the funding is also very, very crucial. So funding or facility is also very crucial. So both part are very, very essential, knowledge and wealth, for the fruitful research. So I put my title as an Environmental Benign Solvents for Ionic Liquid for Sustainable Development, and we'll go through this. Before going that, as Professor Sanjay Kumar informed, that I am from Chemistry Department at IIT Madras. We have a beautiful campus. Please do visit if you have opportunity to visit Chennai or South India, and I will be happy to host you if you are visiting for a few hours or a few days, and please do let me know in advance. And we are 34 people, faculty in this chemistry department, more or less working on 34 emerging fields and the unique fields. Please do visit our website if you want to know further about this. I would like to thank before itself, because at the end we don't know how much time it would be there and we'll be in a hurry. So I would like to thank all my students, those who are in the bold letter. They have been graduated and they are in a faculty position or a postdoc across the globe. And I would like to thank postdocs, MSc project student, and other summer project intern, those who worked in our group in last 10 to 11 years. I would like to thank all my collaborators within the department, within the institute, and within the country and across the globe. Of course, I would like to thank funding agencies, without which the work is not doable, and also the organizers of this conference, and some of the websites from where I took all the some of the images, and I would like to thank them also. So I would like to start the talk with this logo. This is United Nations Sustainable Development Goals logo. If I put a pointer, so it starts with this as a 1 and then all the way up to 17. Goals set by United Nations by 2030, and they are requesting all the societies across the globe and all the academicians and industrial people to work towards this sustainable development. If you ask me what could be the sustainable development, what is the definition in short? So any development which is economically viable, environmentally acceptable, and socially equitable. So that kind of development we can call as a sustainable development. And of course, chemistry has to play a huge role, starting from reactants and during the process and product or the reaction and the product or byproduct, and in every stage, initiation, propagation, and termination. So at every stage, chemistry has to play a huge role, and using environmental benign compounds and also reducing the byproducts and so on. To give one example, in mobile phone alone, what we call smartphone, there are about 50 elements need to be used either in pure or in a mixture form. They might be using in the screen or processor or a case or a battery. So to devise a better and better smartphone, you need to know the chemistry of 50 elements and how they behave in presence of other elements and other compounds. And that's the crucial role chemistry has to play. So other than the chemistry and other than what I told initially, funds and knowledge, we also need a collaboration. Whatever the way today you are expert in one field, that's not enough. We need to look for collaboration, and then only innovations are feasible. And this collaboration must be among academicians, also with their collaboration with industry and the government. So when all three go together, then only innovations are feasible. So while taking care of innovations and the sustainable development keeping in mind, that's where we say if you protect nature, nature will protect you. So how we can do developments without harming the environment, and that is the key. If you see petrochemical based solvent market, annually it is a 4% increase and it's around $57 billion market. And if you see by volume, about 37,500 kilotons of solvents per year. This might be ethylene, propylene, methanol, xylene, benzene, toluene, or other petrochemical based solvent market. And due to high demand in at least three sectors: automotive, construction, and the energy. And these three sectors are the key for large amount of use of petrochemical solvent. However, due to environmental stringent regulations, they are now looking for alternative solvents. And these alternatives may come from bio-derived or the close to the nature. One such solvent I have put it here, that is a serine, and it's a cellulose derived solvent. The cost is an issue, but this can be an alternative solvent in future for replacing many aprotic solvents. Well, so we will see why we need to look for alternative and what is ionic liquid and what is our interest there and what are the recent trends and what is the take home message for all of us. If you see green chemistry principle, what is the green chemistry? I can read it from this definition. The design, the development, and implementation, all three, of chemical product and process that either it should reduce or it should completely eliminate the use or the generation of hazardous substances. So we should not use hazardous substance, we should not generate hazardous substance during entire product and process design, whether it is the starting point or whether it is during the course of reaction or at the end of the reaction. And if you maintain that kind of chemistry or that kind of science, we can call green chemistry. Well, we know 12 green chemistry principle. Today, I will be focusing more on safer solvent and auxiliaries, and other one we can touch up a little bit. Similar to 12 green chemistry principle, we also are aware of 12 principles of green engineering, where today we will focus little bit on prevention instead of treatment, or design for separation, or maximize the efficiency, output pulled versus input pushed, and the renewable rather than depleting. So I spoke so far about three numbers. 1 to 17 United Nations Sustainable Development Goal. It is in short will be called as SDG. And 1 to 12 Principle of Green Chemistry, 1 to 12 Principle of Green Engineering. Today, when any research project or either of multidisciplinary or of international project, the project objectives significantly enhance if you clearly mention what kind of sustainable development goal you are focusing, using what green chemistry and what green chemical engineering or green engineering principle. Well, if you allow me to divide the entire research into 3 categories based on the phase, based on the state of the chemicals: solid state chemistry or solid state science, liquid phase science, and gas phase science. I have no hesitation to tell you that compared to solid phase and the gas phase, liquid phase or bulk phase or solution phase research is dominant due to many reasons. Maybe it is easy to mix it, or uniform heat dissipation, stirring, pumping, or transporting. All these are maintaining the high temperature or maintaining other parameters. It is much easy compared to other 2 phase science, and that could be the reason it is dominant. And once we say the solution phase science or solution phase research is dominant, the solvents are the key, and the solvents are majority, are the portions of in this kind of research. Unfortunately, this solvents represents the large portion of volatile organic compounds, or these are the, due to their high vapor pressure and low water solubility of this kind of solvents, they create so many other problems. Other than facilitating the research better way, this also brings some more problems, and this includes global warming, climate change, ozone depletion, air pollution, human health related issues, to name a few. So what we should do, we should look for other solvents, renewable solvent, or we should use how to minimize the use of this volatile organic compound or less toxic one. Or can we have a solvents with low vapor pressure and high boiling point? So better one is to look for alternative solvents which have low volatility, high stability, and the 3R principle we should always remember. What is that? Reduce, reuse, and recycle. How many times we can recycle them or reuse them is the key. And it should not, when new solvent you are bringing it, it should not lead to another problems. Okay, it should not create another problems. And for any business, similar to our research, what is the motto? Minimum investment, maximum profit. That it mean the replacing solvent should have been low cost and high yield. Well, is this enough? No. When you look for a solvent, you might be looking to promote the chemistry through particular reaction, or you would like to maintain particular pH, or you are interested in removing impurities or byproduct, or partitioning them well, or isolating the product, or dissolving reactants or the products. So solvents play a multiple roles. So in a reaction, when you use a solvent, it's not a single task. It's a multi-task. So I provide you 3 websites. This is the first one, ACS Green Chemistry Institute website, which gives you a full details of the screening. I will tell you in the forthcoming slides. So if you are convinced that yes, we should look for alternative and environmental benign solvents, what are the challenges when we look for? So we need them in different nature, protic, aprotic, different polarity, different basicity, and above all, we need to have a certain combination. For example, we are looking for, let's say, low polarity, high basicity, and aprotic solvent. So when you have more and more restriction, more and more combination, it is difficult. So we cannot, our search become more and more intense, and the probability is becoming narrowed down. So what is a thumb rule when we go for a solvent? How we select the solvent, other than what I told in the previous couple of slides? We look them, what is the temperature window? What is the range between melting point to the boiling point? That is the one thing. And what is the polarity? We know like, dissolve, like, and other thumb rules. And the last but not the least, what kind of functional groups it possesses? Is it compatible or not? So we usually look for temperature window, functional groups, and the polarity. But is it enough? Is this enough when you choose for a solvent for a particular reaction? Definitely not. One heat capacity and so on. And also one should look for their functionality and safety issues, health hazardous issues, environmental impact, and the regulatory impact and the legal controls, and all this has to look, because once your research click and it is giving a good results, your research done at the laboratory will go from laboratory scale to the pilot scale to the industrial scale. So once the scale is going up and up, one need to be careful how it proceed, and whether do we have the possibility of purchasing, not us, or at least the industry, whether they can purchase in our country in the large scale, or whether they can transport from one place to other place without having much regulation and the legal issues. So this is also one has to keep in mind, and their toxicity profile and so on, or how you are going to dispose them if it is coming as a byproduct, or how many times you can recycle or reuse or this region of low polarity with high basicity of aprotic solvent, we don't have any can ask the industry to replace them with the benign solvents. Well, ACS Green Chemistry Institute website came up with the screening of 272 industrially important solvents with the various input parameters, as I told you earlier, properties and point and the pretty. You can use this website to find out more and more environmental friendly compared to what you're using now. However, that is, though you think that 270 is a high number, but I still believe this is a small number. And another website, or it's a Chem21 public private partnership company from Europe, they have divided industrially important organic solvent into 6 categories, from recommended to problem within the same family. Let's say ethers, if you are using diethyl ether, which is highly hazardous, can there are so many parameters, but this thumb rules works in most of the time. At least you know that you are not doing a safe chemistry or a safe research for environment. How to think of replacing. So 272 by this website is more interactive. One can look. So this is a starting point if you are looking for alternative solvents or a cheaper solvent or a better environmental benign solvents. But this number is too small compared to the amount used in the petrochemical solvent. We need to have a much more larger options when you are looking for the replacement. So one such option I put it here is ionic liquids. In a liquid, this is a new class of molten salts known for age. Am I audible? Yeah. So it has a potential to replace volatile organic compound, and it possesses combination of unique properties. For example, vapor pressure is negligible, liquid range is very high, and flammability is very, very low. Electrochemical window is very high for battery and supercapacitor and energy systems. Conductivity is very high, solvating capacity is very high, and above all, great varieties of the structure feasible. So I put another word for this ionic liquid as a hybrid salts. We know the conventional salts, sodium chloride and other, both cation and anion are inorganic nature. If you see here, in ionic liquid, one of them, preferably cation, is organic nature, and most of them are heterocyclic compounds: imidazolium, pyridinium, pyrrolidinium, piperidinium, and so on. And of course, we do have a tetralkyl ammonium and tetralkyl phosphonium also, but they are very bulky and big in size compared to anion. Anions usually are of inorganic nature, and it might be at the smallest like halides, chloride, bromide, iodide, or tetrafluoroborate, hexafluorophosphate, or nitrate, or triflate, or a base triflamide. So based on the cation, anion, and the alkyl chain length attached to cation, theoretically, millions of ionic liquids feasible. Well, will all of them turn into liquid or not? That's another question. But on paper, we can have a millions of ionic liquid feasible. And the predominant reason why they are salts but behave or they possess in the liquid state, one of the main reason is the difference in size and the asymmetry. So the cations are usually bulky and very big, and anions are usually small, and they do have an interaction and they come closer, so would like to be stay together. However, due to large difference in size and asymmetry, they cannot come so close, so will not become a solid. They leave so much void volume, and that is one of the reason that they are liquid at room temperature. If I say that I take a glass of water, add a sodium chloride or meetu or namak or uppu, and dissolve it, can I call this ionic liquid? Answer is no. It's an ionic solution where ions, cation and anions are surrounded by the solvent molecules. What we are talking about ionic liquid, in this magic liquid, the ions are surrounded by their own ions, cations by anions and vice versa. And that's the beauty for them to have a combination of unique properties, and they are multifunctional. So theoretically, millions possible. Even in reality, already thousands have been synthesized, much more than the organic solvents. And they are multifunctional, and they possess unique combination of properties. Having said all these things, if you ask me, sir, can you tell a couple of limitations of these ionic liquids? Well, the first and foremost comes is a viscosity. Viscosity of this class of solvents, ionic liquids, are much larger, or at least little bit larger in some cases. compared to organic solvent. And this viscosity creates a huge problem. Wherever you want ion transport or ion exchange, or mixing ionic liquids. Now, having said these two limitations, but both can be addressed at the same time: viscosity, cost. It is like a ek tir do nishan. How we can address? So instead of using pure organic, pure ionic liquid, you use their mixture either in water or in organic solvents. One side we want to replace organic solvent, and other side we are talking about using them in the mixture. So how we justify? Well, for a same chemical reaction, to achieve the same product or better product, by adding small amount of ionic liquid initial stage, that is also environmental friendly, because without compromising the final product, you are achieving it with the less amount of, or in reducing the quantity required for a given quantity of the product, or so on. So about 2-3 decades ago, when this research started, they were using the solvents which we look for when we look for any solvent. If you see SciFinder, there are more than 86,000 publications, 17,000 plus patents, and about 50 books. And similar numbers you can see by Scopus also, slightly less number probably conference proceedings or the books or book chapter thesis might the number vary, but however, every year there are about 6,000 publications without taking into account the patents. Patents are separate. So how come this field attracted so many people and so many publications? If you see the depth or the popularity of this field just by one paper about 2 decades ago, the review paper published by Tom Welton, who is at Imperial College London and currently he is the president of Royal Society of Chemistry. This single review paper has been cited more than 11,500 times in 20 years. That shows the popularity of this field. So I listed some popular people who published, and Professor Chris Hadeker from UK. I had opportunity to work with them as my postdoc during 2005 to 10. Well, India is not behind, and there are at the 3rd position after China and US. So many people in India working on this research area. I told not less than 150 affiliations. And these are the few affiliations. The top affiliation, I put it here: University of Delhi, BARC Mumbai, NCL Pune, IIT Delhi, IIT Madras, IICT Hyderabad, ICT Mumbai, IIT Kharagpur, CSMCRI Bhavnagar, Banaras Hindu University Varanasi, ISCS Kolkata, Shivaji University Kolhapur, IIT Guwahati, Guru Nanak Dev University Amritsar, IGCAR Kalpakam, and so on. Well, the list is very long. It's around 150. And if you see chemical engineering, material science, physics, biochemistry, toxicology, how a single research field can inspire so many varieties of the researchers. So the answer is not very difficult. Their phase is solution phase research is dominant, and wherever solution phase research solvents are there, and wherever solvents are there, we can talk about ionic liquids. Well, this is not only where ionic liquid has been used or a catalyst or a reactant auxiliary or a performance additive, and this research has gone to the various scale from pilot to commercial scale, and I will tell you the more comprehensive list, show you at the end of my talk. Well, having said so great about this, what is still our intention is how to understand the role of ionic liquid systematically, especially their structure to property, how it is related, and the bulk properties, thermodynamic properties, how this understanding thermodynamic properties and structure property relation will help us to understand the interactions they possess and for the targeted properties for the targeted applications or a task specific application. Well, that's where we devote, and when any research goes from laboratory scale to the pilot and to the commercial and to the industrial scale, their accurate knowledge of thermophysical properties data is essential, because to design cost effective process and product, or what you call the plants or the design of the reactors and so on. And of course this accuracy depends what application you are using, but without this would be the input parameters for chemical engineers to design. Otherwise you cannot design, or you overestimate or underestimate, and this may lead to either loss or the damage or the accidents. So this data is very, very essential. Well, there are so many companies selling ionic liquid in the market nowadays, including TCI, Solvanix, Sigma, Aldrich, Fluga, Cytec, Oilitech, Merck, BASF, and so on. However, we never purchased any ionic liquid from any of this company for two reasons. One, this company sells only well-known ionic liquids, whereas we are interested in the new novel ionic liquid with the unique combination of properties or the task-specific properties. That's the first reason. Second reason, if you synthesize them in the laboratory in small scale, that cost can be reduced predominantly, or at least the study shows that if you synthesize, you buy raw products, raw material, and synthesize them in the laboratory, the cost will be reduced at least 10 times. So because of these two reasons, we synthesize. We are not expert in organic chemistry. However, the synthesis is not very difficult. It is either acid-base neutralization or by metathesis. What is more challenging is purifying them and handling them. Characterization is also not very difficult, but purifying, characterization, handling is much more difficult compared to the synthesis. We were successfully synthesized in last 10 years more than 100 new ionic liquids and more than 50 non-ionic liquids. So we have a library of about 150 ionic liquids, 100 new plus 50 already available in the literature from various classes, but most of them are protic in nature. What is the thumb rule? If for a given ionic liquid, Lewis acidity of the cation source and the Lewis basicity of the anion source both are low, the resulting ionic liquid will be 100% liquid. If both are high, 99.99%, that would be a solid. Only in case of mix and match, one need to look for more chemistry. Otherwise, if both are low, you will get close to 100%, more than 99% around liquid phase only. Also, there are literature available how you can go through ionic crystal to molecular liquid or non-IL to poor IL, and what is a good IL, how this basicity and acidity and the van der Waals forces you can tune, or the source you can consider, so to get the good ionic liquids. Well, what is a good ionic liquid? There is another slide I will tell you later on. These are the few samples synthesized in our laboratory. Most of them are without purification, some of them after purification. So after synthesis, we purify them, then characterize through IR, NMR, and the GC or GCMS, and Carl Fischer titrator, where what is the moisture content we analyze through colorimetric titration. This analysis of ionic liquid is very, very crucial, because small amount or trace amount of water content can influence many properties, especially transport properties like conductivity, ionic conductivity, and the viscosity. So that's why this data is very, very essential. The characterization and the purity of the ionic liquid is most important part in the research of ionic liquid. Whatever the purity, you see, we know that if your starting compound is not 100% pure, you are starting the reaction with the 99% pure chemicals, how you will get 100% pure product? The impurity from your reactant will be there. Or when you try more and more process to remove impurity, as the number of steps are increasing, the chances of contaminating product is more and more. The best way is you mix two reactant, get product, no byproduct, no what you call the processing of cleaning or separating or what you call workup. So minimum amount of chemicals one should use to get the final product. We say that if you see someone cleaning his new vehicle or the new laptop or new mobile with the old cloth, is it advisable or not? The process you want to clean. However, the cloth what you are using is dirty cloth. So you may end up tiny particles on the surface. So instead of cleaning, you may be more contaminating more. So that one has to pay attention. Same thing with the chemistry here. Well, after purifying and characterizing, we study their volumetric properties, transport properties, acoustic properties, and thermal properties, interfacial properties, surface properties, ionic properties, and refractive properties, and then this pure properties measured as a function of temperature and pressure will use for calculating derived properties. And we also study their phase equilibria, solid liquid, that is a solubility, liquid liquid miscibility, and vapor liquid equilibria. And all this data has been used to calculate in the process and product design. This will be an input parameter wherever an engineer or a chemical engineer would like to design what you call process and product design calculations for heat transfer, mass transfer, fluid flow, and separation, and so on. Well, if you recall, in one of the slides I say theoretically millions of ionic liquid feasible. Having said that, we don't have that much time to study all of them. We don't have that much funding, human resources, and chemicals. And to avoid all these things, one need to look up for a certain families and do some research and then develop models, predictive models, or computational models, or the correlations or group contribution methods, or varieties of the models. And this will help us to expand our knowledge of the chemicals and their physical properties for a given application. And I show you some instruments used in our work here, including these are hosted in our laboratory or in departmental facility or the collaborators lab or the institute instrumentation facilities or analytical instrumentation facility center at the institute. If you see carefully, everywhere I wrote accuracy below that. So I strongly feel any science when you do and you get in terms of numbers, your results when you express in terms of numbers, two things are very, very essential. One, units, if it possesses. If it is unitless, that's a different story. If it has units, unit must be presented in what unit these values are. The second one, other than the unit, at what parameter this value has been measured or calculated or derived. So the conditions and the accuracy. First one, units. Second one, the conditions and the accuracy at the confidence level. These are very, very must. Otherwise, the number has no meaning. I strongly feel in science or in research, there is no right and wrong results. Whatever you observe, the result should be one, reproducible in anywhere in the world at the same conditions what you measured, you have done. So it is very, very essential to provide the conditions at which you have obtained these results. So please, I strongly advise very young research scholars and the PhD students and the master students, those who are about to start their career, pay attention. Don't worry that all results should fall on one single line. This will never happen because of various reasons. That might be due to instrumental error, or that might be due to human error, that might be due to calibration, and most predominant error is, many of people will ignore that is not due to human or instrument, that is due to the purity of the compound. If our compound is not 100% pure, how you can expect the property or the results or the data should be 100% accurate? So please pay attention of all these things: human error, instrumental error, calibration error, and the confidence level parameters and the purity of the sample. Well, this is our expertise, and I'm proud of my research group and all the scholars who worked hard for last 10 years. Because of them, we have now proudly say that more than 7,500 data measured in our laboratory at IIT Madras for various ionic liquids and their mixtures has been screened by IUPAC NIST and has been accepted to include in this ionic liquid database IL Thermo. This is a free of charge available database. They update very frequently, but the last update what I took is in June. I'm not sure whether they have updated again recently or not. At least 2 months ago, no. In the beginning of this year, I couldn't get. And this is free of charge, available ilthermo.boulder.nist.gov. And this is very, very important website if one would like to know more about ionic liquid, where you can find more than 2,175 new ionic liquids, old ionic liquids, and their profile. And total data points are more than 7 lakh. I was telling one more thing, how to know good ionic liquid. This is a Walden rule for ionicity. So Walden is a scientist. What he proposed, there is a linear relation between log of molar conductivity versus log of fluidity. This is a 1 by viscosity, fluidity, and this is conductivity, molar conductivity per mole, conductivity per mole. And this is an ideal line. It is a 0.1 molar KCl. It is told that among the salts, K plus and Cl minus size is comparable, very close to each other compared to any other salts. And that 1.1 molar KCl solution is taken as ideal solution or ideal line. Very close to this line is a ideal ionic solution, or we can say good ionic liquid. If it is above, we call super ionic liquid, and if it is below, we call low ionic liquid, and on the line or close to line is a good ionic liquids. So where in the bulk we have 1:1, not in a pairs. So ion pairs are less, but it will be in the ion forms, one cation, one anion are surrounding. Well, one need to understand more computational techniques to know further about this, how ionic liquid is in the bulk, what is the cluster, and how they behave. And this is our expertise. However, now I am going to present all the collaborative works. We do synthesize these varieties of ionic liquid and measure their thorough thermophysical profile. But before even synthesizing, we were looking for a particular property of the ionic liquid for a particular application. And as I told you, it doesn't matter how expert you are in a one field, one has to do collaboration or a multidisciplinary research work. And that's the future. So we have collaborated with various type of researchers, including chemistry, chemical engineering, physics, metallurgy, or biotechnology, and what you call petrochemical engineers, mechanical engineers, and so on. And I will show you how a knowledge of a simple science or a basic science can be used for the applied science or the technology. So first project, I will take around 10-15 minutes, and then we can go for question answer session. So the first application is from Oil India Limited company project. This is along with my colleague, Professor Jitendra Sangwai from a petrochemical engineering, who sits in the ocean engineering department. And we would like to understand in the tank bottom sludge, how small amount of asphaltene holds the large amount of aliphatic and aromatic not to get dissolved in a conventional organic solvents like toluene, heptane, hexane, dodecane, etc. So to understand the role of ionic liquid, how it will help to dissolve or enhance the dissolution of tank bottom sludge. This, if you see the tank bottom here, this you can see a person standing there. It's a very huge. As a part of this project, I got an opportunity to visit Digboy, the first well of crude oil, and I went there in Assam. What do you call crude oil company, Oil India Limited company there, and it was a great experience to see how big this storage tanks, and sometimes more than half of them filled with the tank bottom sludge, and this tank become unusable, and they try various conventional way like a heating coil or a conventional surfactant solutions or other solution, and they still unable to clean them. And I was told that for a cleaning purpose, these tanks sometimes they close for several days to weeks to months and sometimes years also. Not only cleaning is the difficult part, but also where to throw this tank bottom sludge once they dig out. Environmental regulation is issue, and they were told that humans will go inside personally to dig out, because by heating or stirring or pumping or you call sending the surfactant solution or the patented solution, they are unable to clean. While humans will go personally go inside and dig, some places you have a hard surface and all of a sudden you find somewhere soft surface where entire human can sink, and it's a big challenge and risky. Well, that are the problem part. Come to here solution part, what we have done. So we took tank bottom sludge by 1 gram, and the conventional solvent, whatever toluene or dodecane, whatever they were using, same room temperature, stirring speed, or the amount of the solvent ratio is same, everything same. We have dissolved them, and some amount is dissolved, not much. And then we have added 0.1 by mass ionic liquid. So after tank bottom sludge dissolved in a conventional solvent, we consider that as a zero. That is the starting point or the base point, because we only want to understand the role of ionic liquid. and then we added a tiny amount of ionic liquid. This is the ratio is here, and the upper part where more tank bottom sludge is dissolved means here in the upper part, so concentration of sludge will go high, or crude oil concentration will go high. The bottom part, which consists of various things like mud or sand or other undissolved things, here concentration of the crude should go down because crude is more dissolved. And concentration going up, we have measured by UV visible spectroscopy. Concentration going down, we have measured by IR and NMR. Well, you see the results are very astonishing. 0 is crude oil, tank bottom sludge plus conventional solvent, and that is a 0. And after adding tiny amount of ionic liquid, that is a 0.1 ratio, it is going up to 60 to 65% enhancement. Various ionic liquid, various ratios, and various solvents we have tried. Toluene and heptanes are the best solvents, and by adding the ionic liquid, so far BIMIM PF6 we found is a good solvent which enhance 65%. That's a huge. Well, we have confirmed this through UV. We also confirmed this reduction in the bottom part by IR. You can see the stretching frequency and the bending frequency around 1450 and 2950. The black one is for tank bottom sludge. The red one is the tank bottom sludge and the solvent, organic solvent, in this case toluene. And the green one is after adding ionic liquid, in this case BIMIM PF6. So you can see the intensities are going down. That means concentration in the bottom is going down. That means it is dissolving in the upper phase, that is the toluene rich phase. Similar results we also obtained from the IR and NMR. Now it is confirmed that it is happening. Magic is happening with the small amount of ionic liquid, adding 65% enhancement. Now what could be the reason? We proposed with the model asphaltene plausible mechanism that the lone pair of the heteroatoms of the resins might be on nitrogen, sulfur, or oxygen, attacked by the ionic liquid, preferably cation, or we don't know, maybe anion also. So there is ionic liquid, preferably cation, attacked on the lone pair of heteroatoms at the resins or the asphaltene, and then make them to not to bound strongly with the saturates and aromatics. So the saturates and aromatics become comparatively earlier time, it is more free, and the remaining part is done by the solvent, toluene, not by ionic liquid. So ionic liquid is only making them to release, so it's asphaltene not to hold aromatics and aliphatics, and this we proposed. And of course one has to understand more depth through computational or through various spectroscopic. However, we could convince to the reviewers from various journals and the patent office and the thesis examiners. So this research gave 4 papers, 1 thesis, and 2 patents. Well, the second application is enhanced oil recovery. We all know that the natural flooding, that is primary flooding, comes by naturally. After that, researchers do secondary flooding through steam or hot water at the designated places to remove the crude oil from other designated places to push them. And after secondary flooding also, research says that more than 25 or even up to 27 or 30% crude oil still is there underground. And this is very, very important to take out. And that's where we wanted to mimic in the tertiary flooding. And this is the reactor where we do uniform size silica as rocks. And then 1 pore volume is about 100 ml. We take crude oil and first we push with the hot water, because that is a secondary flooding. We want to understand only tertiary flooding. So secondary flooding through hot water, and then tertiary flooding we do with the all conventional things we have tried and optimized. So people do use surfactants, polymers, and conventional salts, and we optimized the better process for a given system and given condition and given crude oil, that the optimized and the best combination gives around 52% recovery. That means you have 100 ml crude, you passed 100 ml water, and the second time you passed 100 ml this solution having SDS, conventional salt, and polymer. So you recovered total 52. Still 48 centimeter cube crude oil is inside. Now we want to push through ionic liquid solution phase. Instead of this phase, second time, instead of this phase, can we add a tiny amount of ionic liquid in ppm level? How much enhancement happen? Instead of 52, the highest amount of crude oil recovered is 72%. That means from the optimized one, by adding a tiny amount of ionic liquid, we'll get 20% enhanced crude oil. That's 20% is a huge. So what could be the reason that? And we checked with the various ionic liquids, various conditions at this where the reactors are there, and more or less every time we are getting 52 to 72, or each time about 20% enhancement. Now, one may think, how tiny amount of ionic liquid is doing magic? Keeping all other things same, surfactant same, polymer same, conventional salt same, and only added tiny amount of ionic liquid. Here is a basic chemistry comes into picture. The interfacial tension is playing a crucial role. The interfacial tension between two things. One, crude oil and the water-rich phase, because the predominant is a hot water or a steam. So crude oil and hot water, where hot water contains various things, including ionic liquid. And then the other one is the tension between the rock and crude. Rock and what you call contact angle or interfacial tension, or a tension between rock and crude, or a contact angle. So, however, rock and crude we have not checked, but we checked the interfacial tension between the water-rich phase and the crude oil. So this is the only pure water and crude oil. You see the interfacial tension values are around 40 millinewton per meter around room temperature, which reduce up to close to 10 millinewton per meter by adding ionic liquid. So addition of ionic liquid reduce the interfacial tension up to 50% or more. That's a very huge number, predominant up to 56% decrease in interfacial tension has been observed. And this is the predominant reason, by adding a tiny amount of ionic liquid, how enhanced oil recovery gone from 52 to 72%. Well, we have so many other applications like metal ion extraction using ionic liquid, or especially aliquot or choline or ammonium based ionic liquid. How tiny amount of ionic liquid can help to extract radioactive materials, americium, europium, or lanthanides and actinides, or especially when they both present in high level liquid waste, where trace amount of radioactive material is trapped in the large quantity of nitric acid solution. And the conventional things is only solvation mechanism. When you add tiny amount of ionic liquid in the conventional thing, in addition to solvation, you have a cation and anion exchange, and that will help you to extract more better. And we checked with the conventional system. This research has been done at the IGCAR using this distribution ratio of americium in the organic phase and aqueous phase is using sodium iodide scintillation detector at IGCAR. Operator only, the technician only operated this. We cannot, but we can watch how he is doing. And you use the conventional methods, all these things. same solvent, same conventional parameters, added only ionic liquid, and we found that the distribution ratios are threefold, where they have a problem of disposing this high level liquid waste in the huge drums, and they have to bury in the deep sea, transporting and calculating that it is safe for a few decades. All this will be very expensive. So if threefold means you can concentrate that solution of radioactive material instead of 3 drums in 1 drum, or if you can separate, can you reuse them? However, this research we have not done much, but the primary results, whatever you use dodecan or toluene, in addition you add tiny amount of ionic liquid in known concentration, much lower than what you take organic solvent, and the extraction or the distribution of americium into one phase is 3 times more than the earlier one. This helps a lot. We also worked on Indo-Spanish project with the mechanical engineers, where vapor absorption refrigeration system we want to run. We were looking for at room temperature and release this ammonia at high temperature, and the temperature has to be raised by the sunlight. Well, we were not succeed much because we were looking for a targeted ionic liquid with high ammonia solubility, low viscosity, non-corrosive, and thermal conductivity high, and economically cheaper. When these two properties you want to address at a time, one, viscosity should low and thermal, what you call decomposition temperature is high, these are contradictory. It is always challenging to have a high thermal decomposition temperature ionic liquid with low viscosity. Well, we have got limited success. I will show in the forthcoming slides. So while we were looking for this kind of ionic liquids, in the literature we know that EDSO4 is the better so far among the various ionic liquids for the ammonia solubility. And we also got some 2 or 3 different group results we have collated from Shiflett group and the Wang group, where they have individually at the different same year, but the different journals and different groups, they have studied same ionic liquid with ammonia solubility, same ionic liquid with water solubility. So we got an idea that to tackle viscosity and the cost at a time, can we club, instead of pure ionic liquid, can we use water as a co-solvent? And instead of designing prototype, we used Aspen and NRTL model and equation of state to get the results. And this is through collaboration with the Professor Venkatrathnan group, and it's a MTech project by Sumit Swarnakar. And we were happy to notice that this is the conventional lithium bromide water system where circulation ratio is very small and coefficient performance is good. With pure ionic liquid and ammonia, coefficient of performance is more or less okay. So the refrigerator is same good. However, circulation ratio is very high. That means equipment size, the refrigerator size is very big, 6 times of the conventional refrigeration system. That is not doable. For a small room, your refrigerating system may be of equal size of room, then you have to put outside the room and run, which is not viable. But when we use water as a co-solvent, coefficient of performance is still comparable, and circulation ratio is significantly reduced, become half. So this is the first results to show that ionic liquid in the refrigeration systems can be used with water or other solvents as a co-solvent. We couldn't go beyond 20% because beyond 20, the water is carrying over in the condenser and evaporator, they may damage them. And these results were successfully published in Applied Thermal Engineering, and it opened up the avenue of the use of ionic liquids, especially in vapor absorption refrigeration system field as a operating fluid. Well, I think I don't have much time now. I will skip remaining applications so we can have a discussion. We were looking for, can we have a much polar liquid than the water? We know that SO3H group and triplet or the triazolium is known to be more polar. So we clubbed this triazolium based ionic liquid having SO3H group in the cation and also triplet as an anion, and our intention came true that these kind of ionic liquid are much more polar than the water and alcohols. Wherever the polarity is the issue in organic reactions or other reactions, these ionic liquids can be used, if not in the pure, but they can mix with alcohols and water to enhance the polarity or to boost the polarity to enhance the product and other way. We have not explored much, but we proved that the polarity is high. And we were the second one next to Ohno group from Japan to relate the polarity or the solvatochromic properties with the refractive properties. And this is one of the very good correlation we have done for various class of protic ionic liquids. And we also look in the engine fluids, conventional therminol, can we have ionic liquids as a heat transfer fluids? And we got significant success. As I told you in one of the earlier slide, viscosity low and thermal decomposition temperature high in the protic class of ionic liquid is very rare. We are happy to say that this is the one of the first kind of protic ionic liquid with dimethyl ethanol amine case of ionic liquid, protic nature with more than 300 decomposition temperature. And all the properties of this kind of ionic liquid as a heat transfer fluids comparable with the conventional therminol heat transfer fluids except the viscosity. All other properties, conductivity, heat capacity, heat storage density, decomposition temperature, all are comparable. We hope in near future we can address this also, if not in a pure or as a mixture, and we can match this as a better engine fluids and so on. We are also working on dye-sensitized solar cells electrolyte. Here the electrolytes most intention is to facilitate this iodide to triiodide redox process, but due to the temperature change in the daylight and the night, these volatile organic compounds expand and contract, and due to this repeated process the cell may leak. To avoid that, we came up with the ionic liquid. I know the Gardas group worked a lot and many other groups worked a lot. And ionic liquid helped this. And to reduce or to address the viscosity issues and the ion transport issues or the redox process facilitating issue, people have come up with the iodized based ionic liquids. So ionic liquid also contain iodine, and this helps the redox process and performance of the dye-sensitized solar cell. We were also working on extraction of value-added products from the bio-waste. And we took many model compounds from amino acids, alkaloids, phenolic compounds. Actual waste we have not taken, but we have proved this can be done with the synthetic or laboratory made waste. And then we have extracted many of these common biomolecules, very tiny or the fundamental biomolecules or very small molecules in the pure state, tryptophan, caffeine, vanilla, and other things. And we believe strongly that even in the real system, in the complex systems, they will possess same kind of nature and helpful. And this follow Hofmeister series, which were initially developed for the protein, but the same thing observed here. We are also working on desulfurization of diesel, not the real fluid, but model fluid and dodecane predominant. And in the literature, we are also working on carbon dioxide absorption. This is comparatively to the conventional system where we use monoethanol amines, and the same process where you convert amine to amine and then extract, and more or less the same process, but ionic liquid facilitate. And we all know that absorption is easy with the simple conventional monoethanol amines. The high cost in the industrial scale is for desorption. So can we address the desorption issues, or can we recycle this ionic liquid or reuse ionic liquid, if not recycle, n number of times and facilitate this? Anyway, this work is in progress. Same work for electrolyte in supercapacitor, cyanide sensing, pre-treatment of biomass, and now we have so much in this corona time. Many people are using so many mobiles or laptops, or so much e-waste is now generated, these PCBs, and this may contain small amount of metals like gold, silver, copper in various salt form. Can we extract them? So from PCB waste, can we extract this metallic fraction and non-metallic fraction, or can we decrease the e-waste? Anyway, so I showed you overview of so many things, but to summarize, our expertise is designing ionic liquid for targeted properties and study their thermophysical profile, and extensively contribute to their database, precise and accurate data which are essential when they go for process and product design, and collaborate with the various engineers and scientists, and to use these task specific properties of ionic liquid for a particular applications. And I showed successfully how basic science can be used in collaboration for a technological applications, and how ionic liquid as an additive, as an extractant, or as a small quantity can be used within the existing system and reduce the amount of organic solvent required or enhance the product, how this will be useful. And this is the slide I was telling. This is from Mark Shiflett. He was in a company, I think DuPont, for several years, and now in the last few years he's joined University of Kansas in USA as a faculty. Very few people come from industry to academia. We know many people go from academia to industry, but he is one of the key person who came from industry to academia and using ionic liquids directly for industrial scale. And his book just published before Corona in March 2020, about 1 year ago, and included so many processes up to 1 year before that, March 19. So many applications at pilot scale and commercial scale, and he told that there are much more in the pipeline, and the companies are waiting for a patents for the approval, so they didn't allow him to publish here. But this field has a great future in this current decade and near future. Well, take home message is, theoretically millions of ionic liquids feasible. In research you can find for alternative for anything or any solvent, if not for any solvent, at least for many solvents. And this is the dream ionic liquid I tell my students. And this is nothing but it's a quote or a suggestion for youngsters: be positive, no negative. And I feel strongly the future is collaboration, future is multidisciplinary, and the human kind may face significant challenge in the coming decades in these 5 fields, and the research should be done predominantly directly or indirectly related to these 5 fields: energy, environment, water, food, and health. When you work on these 5 fields directly or indirectly, and you club with the sustainability, keeping the environment in mind, keeping the 3R principle: reduce, reuse, and recycle issue, or circular economy, or the sustainability, or eco-friendly, or bio-friendly, this kind of things if you keep in mind. And as a chemist, we all have to play an important role, and the chemist has to play a key role in all these 5 sectors, keeping sustainability an issue. I hope I convinced little bit and justified my title for this VChem talk, and I sincerely thank organizers and thank you all for the patience last 1 hour 20 minutes. And you do write questions to me, you can ask me now, or do write to me at my email GARDAS, that is my last name, Gardas, at iitm.ac.in. Thank you all for listening patiently.
Thank you very much, Professor Gardas, for a very wonderful and very elaborative talk on the ionic liquids. And since we all know that widespread use of volatile organic compounds in many industrial chemical processes is an issue of great environmental concern. So it is an extremely important task to search a potentially green and environmentally friendly alternatives for volatile organic compounds. And believe me, when we talk about green chemistry and sustainability, and when we talk thought process, which is very well taken from the scientific community. And in today's talk, you included the brief introduction of ionic liquids and understanding unique thermophysical properties of novel ionic liquids for metal ion extraction, carbon dioxide capture, desulfurization, biphasic systems for the extraction of value-added products. So it was very good, very wonderful, and very knowledgeable talk.
You're muted, sir. Professor
Hello,
Sanjay,
hello.
yeah.
I'm sorry. First of all, I would like to thank Professor Gardas for this very wonderful inaugural talk. And we are thankful to him for making this talk, this session a huge success. And Professor Gardas, we have received many questions, so we are taking few of them.
Sure.
The first question I received: any specific type of ionic liquid that can be used for the extraction of volatile phytochemicals from plants to get essential oils?
Okay, it's a very general question, and my answer will be also general. I hope I will justify. It depends what kind of chemical compound you want to extract. Whether it can be extracted by pi-pi interaction, or you want aromatic ring, or you want certain polarity. So accordingly, you can tune and design your ionic liquid, keeping in mind both functional groups and the aromaticity or the pi rings, or and then what you call the other properties like viscosity is a key or not. So when we, as I told you, we want to extract biomolecules from the waste, value added product from the waste, we always see the structure of our target compounds. And if at all pre-knowledge of extraction is there, what is the driving force? Is it the similarity in the structure, or is it the dissolving? We want to dissolve them, and accordingly you have to design that kind of cation or anion or that kind of properties in your ionic liquid. So it is doable. You need to understand slightly chemistry of the extraction of your targeted compound and tune the properties of your ionic liquid, especially the polarity and the functional group and the hydrophobicity or the hydrophilicity, and accordingly you can.
Absolutely.
It's not complete trial and error method, though it sounds like is it a trial and error method? I would say not completely, but it is based on some scientific knowledge, trial error method.
Okay.
Yes, please.
In today's talk, Professor Gardas elaborately discussed and included the brief introduction of ionic liquids and understanding unique thermophysical properties of novel ionic liquids for metal ion extraction, carbon dioxide capture, desulfurization of fuels, and aqueous biophysics system for the extraction of value-added products. So I think So I think it's time to take the second question. Am I audible, Professor Gardas?
Yeah. Yes, please.
Okay. Second question is in terms of toxicity issues come from ionic liquids. What is your opinion, especially on the uses related to food?
Well, it's a very good question. I will not say in terms of food, but I will talk generally. We can't label any kind of compounds without thorough research, either toxic or non-toxic. So we have to prove whether they are toxic or non-toxic. And ionic liquids, such a huge class now. Let me take one example, little bit deviate from my answer, and I will come back to one answer. We all know benzene is carcinogenic and toxic. We all know that benzene is organic solvent. Can I generalize, keeping these two statements combining, all organic solvents are carcinogenic and toxic? I can't, because the field is so vast. Same with the ionic liquid. Ionic liquid field is now so vast, you can't generalize that all ionic liquids are green, all ionic liquids are toxic. Both are wrong. All ionic liquids are green is a wrong statement. All ionic liquids are toxic is a wrong statement. The correct statement is, to label anything, we need to study their toxicity profile. Well,
Absolutely.
Having said this, most of the ionic liquids are bio-friendly or eco-friendly and environmental benign and non-toxic. So based on the majority, we are saying this, but we can't label this as a generalized. And in one of the conference, Professor Robin Rogers from Alabama, he requested and pleaded all the community of the ionic liquid, please stop using the general statement that ionic liquids are green. There are some ionic liquids are much more toxic. So now, for a particular research, when you start writing your article or a book chapter or a thesis, you talk about your class of ionic liquid or the class what you have really checked. Or you say that based on the nature of cation and anion, you feel that this might be non-toxic because both the starting compounds are non-toxic to be known. But you can't say that our ionic liquids are green or non-toxic unless you do IC50 study, octanol water partition coefficients, and the toxicity profile and everything. So to answer straightforward to the food science, it depends on what kind of ionic liquid you have chosen. Yes, there are very few ionic liquid which has gone into the food industry as well.
Very well said. Very well said. And again, I'm repeating the same which Professor Gardas just told, especially to the young researchers and research scholars who are listening us through this webinar, that all ionic liquids are not simply green solvents. You cannot label all the ionic liquids as green solvents. So it depends on the case to case, and as per the characteristics and conditions of the reactions, then only you will decide whether it is green or not. Professor, next question is how to choose the good ionic liquid to serve as green catalyst for organic synthesis, especially reactions such as novagenol and bignanyl.
Yeah, good is a subjective. Okay, so good is a subjective, depend on the reaction. So whether you want to reduce the amount of reactant, or you want to reduce the time taken, or you want to enhance the product, if you see the green chemistry principle or any business model, what we want, minimum investment, maximum profit. So in this case, I believe when you say good, you are looking for a catalyst which enhance the yield, or which reduce the byproduct, or which make the environmental condition or the reaction conditions close to the room temperature. Let's say if you do reaction at atmospheric temperature and atmospheric pressure and getting yield better way, that is a good catalyst. That is a thumb rule. So it depends on what reactions you are going to use. And moreover, more than the yield what you get, the most important part is, can you reuse this ionic liquid? Can you recycle this ionic liquid? That is the where the circularity, that is the key point, and that is the challenging, and that's where the research is progressing now. So the good or not good depends on many things. If you can reuse n number of times, if you can't recycle, reuse probably simpler compared to recycle. And in all these energy calculations, for a given amount of product, how much energy or how much amount of amount you are putting is also, atom economy is essential, reaction conditions are essential. So one has to keep all these 12 green chemistry principle and 12 green engineering principle in mind, and also 3R principle: reduce,
Exactly.
reuse, and recycle. If you can address
Exactly.
all three, that is the best. We call Sone Pe Suhaga.
Very good, very good. And there are so many questions, Professor, but we are having less time. So it is the last question which I am asking. Is it possible that the ionic liquid binds activated carbon through surface reaction and use it for adsorbent for removal of organic compounds in solution?
We have not done, but it is possible. There are many research groups are doing on that. And I know I'm giving very general answer, but the questions are also general, so I can't do much. It is doable. Many people are working on this field using ionic liquid as adsorption. But as I told you earlier, it's not only adsorption or absorption. What next? How you get back your compound? Desorption also very, very important. So absorption alone is not the key. How you get back your compound and reuse n number of times, that's the challenging, and that's what it is. See, there are so many carbon compounds or other compounds you can absorb, but for research purpose or a one paper purpose, it is okay. But will it go to industrial scale? Is it viable? Are you talking about the economy? Are you talking about the industrial scale, large scale? Are you addressing the circularity question? Are you addressing the sustainability question? This, as a basic researchers, once we start thinking, we may not get all answer at a time, no problem. At least this question should be in our mind, and before reviewer asks, we should try to address. And that's where the quality of the paper or a thesis or a book will enhance. We know the problems, but we don't know the answer. At least you present that these are the futures can be enhanced. So to straightforward answer is yes, doable. Many research are doing, we are not doing. But more than the adsorption or the separation, please address or try to address the next question: how to reuse them.
Thank you very much, Professor, for answering all the questions. As Professor rightly said at the end of his talk, that when we talk about sustainability, when we talk about environmental sustainability or green chemistry, there are 5 major points which are quite interrelated. Whenever we talk about energy, environment, water, food, and health, these 5 points are quite related. And if someone is addressing one point, it may be related to other 4 points. Or for example, if you are talking about food, then obviously you may talk about water. If you're talking about water, it may be related with the energy and environment indirectly or directly. So there is a lot of things which we can do collectively. And Professor Gardas rightly highlighted that this is the age of collaboration. When you start doing research in collaboration, when you start thinking in a coordinated manner, it gives more results in less time, and all those results are beneficial to everybody. So Professor Gardas, I thank once again from the bottom of our heart for this inaugural talk. Now I request all the participants to please switch on your videos so that we can click a photograph. I request you all to please switch on your videos. And after this photo session, we'll send a link in your chat box for a feedback form. And after submission of the feedback form, you will receive a certificate of the participation.
Happy to see that we crossed the century. More than 100 people are here.
It's only because of you, Professor. People are quite interested in listening you, and you will not believe I have a very long list of questions, but due to a shortage of time, I'm not able to ask all the questions.
By email, I will try to answer.
I'll definitely.
Yeah.
I'll definitely send you all the questions through mail. So
yeah, that will be a learning process. We will also
absolutely. And Professor, when we learn together, when we grow together, it is win-win situation for everybody. Plus, it is beneficial for the scientific community at large. And if we all are working for the sustainability of the environment,
anybody from outside India, Professor Sanjay, do we have participants from outside India?
Professor, more than 80% participants from out of India, from more than 80%. So it is a quite successful webinar.
When I said good morning, I could have said good morning, good afternoon, and good evening.
Absolutely. All three are valid: morning, evening, and afternoon. And the participation itself reflects the success of the webinar, as well as the acceptance of RASAYAN Journal of Chemistry, how it is popular and how people love it. So I will share with you the statistics. More than 80% participation is out of the country, out of the India. So I must thank all the participants for sparing their valuable time to attend this webinar. And we are going to share a link for feedback form in chat box. So you all are requested to please submit your feedback so that we can issue your participation certificate. Thank you very much, one and all. And I especially thank Professor Gardas for sparing time from his busy schedule. And Professor Gardas, I have no words to express my gratitude that you have made this inaugural session a huge success. Thank you very much.
Stay safe and take care. And now in the digital world, stay digital and stay connected. Take care. Bye. I'm signing off, Professor Sanjay Kumar. Thank you. Thank you all.
Sure. Thank you, sir. Thank you very much. So thank you very much, participants. Hope you have received the feedback link in the chat box. You please submit your feedback, issue the participation certificate. That will be visible for next 5 minutes only. Thank you. Hello, am I audible? So I once again thank all the participants for sparing time. Maybe most of you people I am introducing first time through this webinar. And I express my gratitude to all of you to give cooperation and support to the journal and making this journal a huge success. So thank you very much. Now we are ending the meeting. Thanks a lot.